Welcome back to Calculus 3. We are in section 6.3 about the fundamental theorem of line integrals. This is the formal statement. And basically, I hope you understand, it says the line integral of vector field, it is the difference of the potential function at the upper bound and the lower bound. The gradient really it is for vector field, and when the vector field it is a gradient, it is a conservative vector field. So fundamental theorem of line integral, it is the result, the general conclusion for a conservative vector field. And in our next lecture, we will have somewhat more generalized conclusion, Green theorem. Well, I cannot say it's more generalized. It covers another aspect of the line integral. When you have line integral over on a closed curve, that is for the Green theorem. But anyway, for now, let's just focus on fundamental theorem of line integrals. It is for a conservative vector field. And also, we did a calculation. This is an example on the textbook. This is using the definition. And this second method, it is using the fundamental theorem of line integrals. We do get the same conclusion. And in general, it is just true. The fundamental theorem of line integral is more efficient compared to definition. And also some other things you may want to understand the fundamental theorem of line integrals. The first comment I have here is the fundamental theorem of line integral, it is path independent if the vector field it is conservative. Because you look at, this is really the fundamental theorem of line integrals. Okay, line integral, it is for a vector field moving, well, the work done by a vector field along a curve. And then the fundamental theorem of line integral simply says, well, regardless the curve, as long as the vector field it is conservative, and then regardless the curve, you only need to calculate the line integral as the difference of the potential function. So the curve really, it is irrelevant. It's not important anymore. So we said for a conservative vector field, the line integral, it is path independent. It doesn't matter for any curve. Okay. The second comment I have, well, sometimes we do consider the line integral on a closed curve. Remember the curve, several situations we mentioned for the curve, simply connected region. This is a closed curve I'm talking about. This is this kind of thing. Okay, simply simple and closed curve. And then when you consider a line integral on a simple and closed curve, it turns out to be zero. And somewhat those two conclusions, they may look different, but anyway, they are saying the same thing. That's all about the extension from the fundamental theorem of line integrals. Fundamental theorem of line integrals. Okay, let's do a little bit more work about the fundamental theorem of line integrals. The more work part I'm talking about here is, well, for the conservative vector field, I suppose we do know how to check the conservativity. How we know if a vector field it is conservative using cross partial derivatives. The real issue is how do we find out if we do know it is conservative? Then how do we find out a potential function? Okay, so this is again the example from textbook 6.31. We do have the vector field given, and in the beginning, I guess we really don't know if it is conservative or not. So what I did here is, you still can check using the cross partial derivative. Okay, the cross partial derivative here would be 6xy squared. And for the part of q part, 6xy squared again. The cross partial derivatives are the sign, which means the vector field, it is conservative. And then to find out the potential function, what I just said here is, let's say this lowercase f is the potential, which means the vector field, it is the gradient, which really means f sub x, it is 2xy cubed. F sub y, it is this part, because this is how the gradient is formed, right? And then starting from f sub x, when we integrate f sub x with respect to x, okay, so the antiderivative would be antiderivative 2x as x squared, and y cubed, that's a constant, so it still stays. And usually when we consider antiderivative, we just put an arbitrary constant in the end. But anyway, this time you want to be very careful. The potential, suppose this is a potential function. Really, it is a function of two variables. The way we calculate the partial derivative, well, for example, when we consider partial derivative with respect to x, then y is a constant. So at this moment, you want to be very careful. The constant I put here in the end could be a function of y. So I simply denote this as h of y. It's not the constant in the ordinary sense. The constant with partial derivatives. Partial derivatives, that's what I'm saying. This is very important, okay. And then, given the potential function in this fashion, there's a great uncertainty here, right? Because this constant part really is a function of y. So what I did next here is I calculated the partial derivative of this function with respect to y. So that would be 3x squared y squared, then h prime of y. F sub y, I calculated f sub y. F sub y, okay. F sub y, according to this part of calculation, would be 3x squared y squared plus h prime of y. But we do know, because the gradient, okay, we do know the gradient supposedly for this scalar valued function. It is already given. So would it make sense to you, those two partial derivatives, they are observed differently, but anyway, they got to be the same, which really means that h prime of y is cosine of y. H prime of y is cosine of y. So accordingly, h of y, it is sine of y plus a constant. And also keep in mind, this time we are really working with function of y only, function of y only. So this is C, really it is an arbitrary constant here, okay. And indeed, I want you to know a potential function like antiderivatives. There are many, given a conservative vector field, there are many potential functions. And usually for simplicity, we just take the arbitrary constant in the end as 0. So this is a potential function. This is a potential function here. And this is in general how we find out a potential function. And also, I think I just copied and pasted those steps from the textbook. Okay. And we want to find, this is the general strategy, how to find out a potential function for a two-dimensional conservative vector field. F is given as P and Q. And then you want to, first of all, you integrate with respect to X, of this P with respect to X. And then usually you are going to have a function of two variables, of X and Y, and also plus h of y. H of y, it is a constant with respect to x, but indeed, very likely it is a function of y. Okay, then h of y is unknown. And then starting from here, this is supposed to be the potential. So we calculated the partial derivative with respect to y of this supposedly potential function. And usually you're going to have g sub y of x and y, then h prime of y, h prime, this is h prime of y. Okay. And then this g sub y really has to be comparable with partial derivative with respect to y. This is a gradient, right? So it has to be comparable with f sub y, f sub y. They have to be comparable. G sub y here, okay. And they have to be comparable, okay. And then finally, we can find out this h prime of y, h prime of y. And then from h prime, we can find out h, okay. And then finally, any function in the fashion of g of x and y plus h of y, that would be potential. And again, usually we just take this constant as 0, see the arbitrary constant. Because when you use the potential to calculate a line integral, it is always the difference of the line, same line integral at the upper bound and lower bound. So the constant part really doesn't matter. But anyway, for easiness, we just take the constant as 0. So this is in general what we have for what we can do to find out the potential of a conservative vector field. And I suppose I got two big things covered in this section. First, it is the so-called fundamental theorem of line integrals. Second, it is the strategies to find out the potential function. Because most likely from now on, when we calculate the line integral, we are going to use the fundamental theorem of line integrals. Or really, that's all about the potential. And also, I want to know I do have some problems from the text from the assignment list directly. So this is exercise 105. I believe it is on the assignment sheet. It is on the list of the assignment. And also, I think I might have another one here. Or maybe that's it. Yeah, this is exercise 105. It is on the assignment list. Okay, so if needed, do take a look. And also, again, if you have questions, send them an email or stop by those drop-in sessions, and we will start from there. Thank you for watching.